Hello everyone, welcome to this lecture. So, we have seen the definition of oblivious transfer, and our next goal will be to construct oblivious transfer protocols. So, with that goal in mind, we will see in today's lecture about RSA assumption, the RSA problem and the hardcore bit of RSA function. So, most of the things that I am going to discuss in today's lecture are taken from my other NPTEL course on foundations of cryptography. So, if you want to know more details about RSA assumption, RSA function, how hard it is, etc., then you are referred to that other course. The material in the other course, I will be just briefly going through whatever we need for the construction of the oblivious transfer protocol. Okay. So, we start with the set Zn star and its properties. So, what is the set Zn star? So, first of all, the set Zn, where n is a modulus, is the set 0, 1 up to n minus 1. You can imagine that it is the set of all possible remainders which you can obtain by dividing any integer by a given modulus n. So, n is the modulus here. So, that is the definition of Zn. Now, what is Zn star? Zn star is a subset of Zn which has only those elements which are relatively prime or co-prime to the modulus n. Namely, it is the collection of all the integers p from the set Zn such that the GCD, the greatest common divisor of the number b and the modulus n is 1. So, for instance, if I take n is equal to 10, then Z10 star will have the elements 1, 3, 7 and 9, because if you take GCD of 1 and 10, then that is 1, GCD of 3 and 10, that is 1, and so on. But 2 is not a member of Z10 star, because the GCD of 2 and 10 is not 1, it is 2. Okay. And it is easy to see that if the modulus n is a prime number, then Zn star will have all the elements from Zn except 0. Okay. So, we have several nice properties related to the set Zn star. I will quickly state those statements. I will not be going through the proof of these statements. Again, for the proof you are referred to the my NPTEL course on foundations of cryptography. So, if we consider the set Zn star and the operation multiplication modulo n, then it constitutes a group. In fact, we have seen the proof of this particular theorem at the beginning of this course itself, where we discussed about groups and their properties, and we have seen various candidate groups. So, this operation multiplication modulo n is as follows. So, if you have two numbers a and b and you want to compute the result of a multiplication a multiplied with b modulo n, then this is same as you multiply a and b and then take mod n. Whatever is the remainder, that will be considered as the result of a multiplication b modulo n. And we do have efficient algorithms to compute what we call as the multiplicative inverse of any element from the set Zn star, namely the extended Euclid's algorithm can be used to compute the multiplicative inverse of any element from the set Zn star. We also have some nice properties regarding the cardinality of the set Zn star, namely how many integers are relatively co-prime to the modulus n. The cardinality or the number of such elements is denoted by this phi function, which is also called as Euler-Toten function, and the particular cases in which we are interested with respect to this Euler-Toten function are when the number or the modulus n is a prime, in which case the cardinality of phi of n will be p minus 1, whereas if n is the product of distinct prime numbers p and q, then the value of phi of n is the product of p minus 1 and q minus 1. We also have this nice result from the number theory, which says that you take any element a from the set Zn star, and if you compute a to the power phi of n and then take mod n, that will give you the result 1. Okay. And because of this we come to the following conclusion. If you are given any element a from the set Z n star and you want to compute a to the power x modulo n, then the exponent x itself can be reduced modulo phi of n. That means, whatever is the result that you obtain by computing a to the power x modulo n, namely by dividing a to the power x mod n, namely by dividing a to the power x by the modulus n, the same result you will obtain if you first reduce the exponent to x modulo phi of n and then compute a to the power new modulus a to the power in a new remainder modulo n. Okay. So, if y is equal to x modulo phi of n, then what I am saying here is that a to the power x modulo n will give you the same result as a to the power y modulo n. And this is a very nice result, because if your exponent is very large, then instead of computing a to the power a large exponent, you can first reduce the exponent and make it a small value, okay, and then compute modulo n, you will get the same result. Now, based on all these results from number theory, we next discuss the RSA permutation or the RSA bijection, which is a function from the set Z n star to Z n star, and how this function is computed. It is computed as follows. So, here we will be given an exponent e which is greater than 2, and this e is co-prime to phi of n. Now, since it is co-prime to phi of n, again using basic results from number theory, we can conclude that we can find out the inverse of E. Inverse of E exists, inverse of E modulo phi of n exists, let D be that inverse. So, if D is the inverse of E, then we have the property that E times D modulo phi of n is 1, and since D is the inverse of E, other way around, E is the inverse of D. That means, I can say that even D times E modulo phi of n is 1. Now, the way we define this RSA permutation is as follows. So, we have a function from Z n star to Z n star operated with respect to this exponent e, and if you want to compute the value of this function on the input x, then you basically compute x to the power e modulo n, namely the eth power of x modulo n. Whereas, if you want to go back from an element y, then you operate with d, and to compute the inverse of y, we basically compute y to the power d modulo n. Okay. And again, we can prove that the function f sub d is the inverse of the function f sub e. How we can prove that? So, we consider any arbitrary element x, okay, and let y be the image of that x as per the f sub e function. That means, y is equal to x to the power e modulo n, and now we want to prove that we can reverse the effect of the function f sub e by applying the function f sub d on the result of the function f sub e. So, what is the result of the function f sub e? It is y. So, let us see we can reverse the effect by computing the function f sub d on the input y. So, if we want to compute the result, it will be y to the power d modulo n, but y itself is x power e modulo n. So, let me substitute the value of y here. If I substitute, then I get this expression, and then I can take this exponent inside. Overall, I get x to the power e times d modulo n, and now you remember we have this result that if you want to compute x to the power any exponent modulo n, then you can reduce the exponent modulo phi of n. Okay. You will get the same result. So, this will give you the same result as x to the power the exponent e d being reduced modulo phi of n, and then in the base you have mod of phi of n, mod of n. But what we can say about this quantity e times d modulo phi of n, e times d modulo phi of n is 1, because d and e are inverse of each other. So, E times D modulo n will be 1, that means the reduced exponent is now just 1 and x to the power 1 modulo n will be x only. Why so? Because x is an element of z n star, and since x is an element of z n star, it is strictly less than n, and hence the effect of mod will not take place at all when you are computing x modulo n, because you are not doing the wraparound, and hence the result will be x only. So, that shows that these two functions are inverse of each other. If you go from x to y and you want to invert, apply the function f sub d, whereas if suppose you have gone from y to x and then again you want to come back to y, you apply the function f sub e. Okay. Moreover, we can also prove that this function f sub e is a bijection. Okay. And for showing the bijection, let us consider an arbitrary pair of inputs x 1 and x 2, arbitrary elements x 1 and x 2 from the set z n star. And suppose the mapping of x 1 as per the function f sub e is y 1, the mapping of function x 2 as per the function f sub e is y 2, okay, such that y 1 and y 2 are same. Then we want to conclude that x 1 and x 2 are also same. Okay. How do we conclude that? So, since the mapping of x 1 is y 1, I can write y 1 as x 1 power e modulo n, and the mapping of x 2 is y 2, I can write y 2 as x 2 raised to the power e modulo n, but we are assuming that y 1 and y 2 are same. So, hence this equality holds. Now, if this equality holds, then I can also raise both the sides to the exponent d, the same exponent, because if you have LHS equal to RHS, then you raise both the sides to the exponent d, you should get back the same answer. And now, what I can say about x 1 power e d modulo n? Well, x 1 power e d modulo n will be x 1 in the exponent, I can reduce e d as e d modulo phi of n, and e d modulo phi of n will be 1. So, it will give me x 1 only, because x 1 is an element of z n star. So, it is strictly less than n. In the same way, x 2 to the power e d modulo n will be same as in the exponent I reduce e d to modulo phi of n, e d modulo phi of n is 1. So, this is same as x 2. Okay. So, I come to the conclusion that x 1 is equal to x 2. Okay. And since we have shown that the function f e is invertible, okay, that establishes the fact that this function f sub e is a bijection. Okay. So, now based on all this, let us see the RSA problem and the associated assumption, which we call as RSA assumption. So, this problem is defined with respect to an algorithm which we call as Gen RSA, which is publicly known. Lambda here is your security parameter. So, again all these terms might look like a jargon, but you refer to the earlier course on foundations of cryptography. There we have defined what is security parameter, Gen RSA function, and so on. Okay. So, this algorithm Gen RSA outputs some parameters. How the parameters are generated here? So, we first generate the modulus, and to generate the modulus we pick two random prime numbers, random lambda bit prime numbers, distinct prime numbers p and q, and n is said to be the product of p and q. Now, since n is the product of distinct primes p and n, we know that the value of phi of n is the product of p minus 1 and q minus 1. Then as part of this Gen RSA, we select a value e which is greater than 2, such that e is relatively prime to phi of n. If it is relatively prime to phi of n and we know the value of phi of n, then by running the extended Euclid's algorithm we can compute its multiplicative inverse, call it d, and then the output of this Gen RSA algorithm is this 5 tuple, namely the modulus n, its prime factors, the exponent e, and its multiplicative inverse, the exponent e. And what is an RSA problem instance? The RSA problem instance is as follows. You will be given only the value of n and only the exponent e. The values of the prime factors of n and the exponent d, they will not be given to you. And you will be given a challenge instance, namely a random element y from the set z n star, and your goal will be to compute the eth root of this element y, namely y raised to power 1 over e modulo n. Now, y raised to power 1 over e is basically y to the power d modulo n, because 1 over e is d, because d and e are inverse of each other. So, the challenge is you know n, you know y, you are not given d, you are not given the prime factors p and q, and your goal is to come up with the result of y to the power d modulo n. If I give you the prime factors, then this problem is very easy, right. If I give you the prime factors p and q, then you yourself can compute the value of phi of n, and if you know phi of n and you know e, you yourself can compute d, and then you can compute y to the power d modulo n. The challenge is that in the absence of the prime factors of n, or without the knowledge of the exponent t or the knowledge of phi of n, you are supposed to find out y to the power d modulo n. So, this difficulty is formalized by this experiment. Again, this might look like a vague experiment for the people who are taking this course, but if you have gone through foundations of crypto course, then we know how to model various difficult problems in terms of security game. So, in this security game, we have this probabilistic polynomial time adversary, and we have a verifier. The verifier presents an instance of the problem, namely it runs the gen RSA algorithm and generates all the parameters. It picks a random element y from the set z n star, and it creates a challenge instance for the adversary. The challenge instance is the value of the public modulus, the exponent, and the random element y, and the challenge for this adversary is to come up with the value of y to the power d modulo n in polynomial amount of time. Okay. So, he knows that y to the power d modulo n has to be an element of z n star. So, his response should be some element of z n star. How he has computed that response, we do not know. Now, we will say that he has solved the RSA problem, or he has won the experiment, which is denoted by saying that the output of this experiment is 1, if and only if he has indeed computed y to the power d modulo n correctly. That means, the x that he is submitting as a response for his challenge has the property that x to the power e modulo n is indeed equal to y. Otherwise, we will say that he has lost the game, or equivalently the output of the experiment is 0. And we say that RSA assumption holds with respect to the gen RSA algorithm. If for any adversary, any algorithm who is given an instance, a random instance of RSA problem, the probability that he can solve the problem instance, or he can come up with the correct x without the knowledge of the prime factors and d and phi of n, is upper bounded by some negligible function in the security parameter. Okay. Now, based on the RSA assumption, let us next define what we call as RSA hardcore bit, or RSA hardcore function, RSA hardcore predicate. And the intuition here is the following. The claim is that if I give you the output of the RSA function, by RSA function I mean the output of the FE function on some random input, that means I pick a value x randomly, but I do not tell you the value of x, but I give you the value y. You know the value of n, you know the value of e, everything you know. You also know the description of f of e function, that also you know, but you do not know the value of prime factors of n, phi of n, d, and so on. Now, the intuition behind the hardcore RSA hardcore bit is the following. We can prove that if I give you the output of the RSA function on a random input x, then in polynomial amount of time it is difficult to compute the LSB of x. Of course, you will know that LSB of x will be either 0 or 1. So, with probability half you can always guess that okay, the LSB of x is 0 or 1. You toss a coin, a fair coin, and whatever the coin toss gives you as output, you label it as the outcome of the, or you label it as the LSB of x, and probability half you might be correct as well. What the RSA hardcore predicate says is that you cannot do anything better than that. There is no polynomial time algorithm using which you can analyze the output y and come up with the exact LSB of x with probability better than half. So, again we can model this intuition through an experiment which I call as RSA hardcore experiment, which is played between a verifier and a probabilistic polynomial time adversary, whose goal will be to compute the RSA hardcore bit. The verifier will generate the RSA parameters by running the gen RSA function. So, he will generate first the prime factors, compute the modulus, then he picks the public exponent, and once he knows the value of phi of n and e, he can compute d. And now he prepares the challenge instance. So, he picks a random element x from the set z n star, and y is the result of f of x. So, actually it should be f of f sub e x, okay. Namely this is x to the power e modulo n. The verifier can compute this because he has x, he has e, he has n, and now he throws the challenge instance to the adversary. So, he gives the adversary or the algorithm who wants to compute the hardcore bit, the modulus, the public exponent, and the output y. This adversary, he knows that f of e is a function from z n star to z n star. He knows that detail, and he also know that how x would have been converted into y, but he does not know the value of x. X is not given to him. Now, his goal is to come up with the LSB of x in polynomial amount of time. We do not know what strategy he is going to use. So, he submits a response, it is going to be a bit, and we will say that he has won the experiment, or equivalently the output of the experiment is 1, which also means that he is able to solve or compute the RSA hardcore bit if indeed the LSB of this random x, which is not known to the adversary, turns out to be b. And we will say that computing the LSB of x indeed constitutes a hardcore predicate if for every polynomial time adversary participating in the above experiment there is a negligible function such that the probability that that adversary can win the experiment or correctly computes the LSB of x is upper bounded by half plus negligible function. Okay. That means, he should not be able to do anything significantly better than probability half. And it has been proved that indeed that this computing the LSB of x just based on the output of that random x as per the RSA function indeed is difficult to compute in polynomial amount of time. That beautiful result has been published in this paper, which shows that computing the LSB of x is as difficult as computing the entire x based on the result of x to the power e modulo n. Okay. So, I end today's lecture with this. So, we have discussed in today's lecture the RSA assumption, the RSA permutation, and the RSA hardcore bit. Based on all these things, in the next lecture we will see how we can construct a 1 out of 2 OT protocol, a very simple 1 out of 2 OT protocol designed for the case when the sender's inputs are bits. Thank you.